Hello everyone, welcome to my channel. My name is Rishabh and today we will be going to discuss about this very cool and amazing project, that is calibration and augmented reality. So in this project, our task is to develop a program that can calibrate a camera and use the calibration data to generate virtual objects in a scene. So to calibrate the camera, we will be needing internal parameters of the camera, such as the focal length and distortion coefficients. For our project, we will use checkerboard image for calibration, and once the camera is calibrated, our program should be able to detect the target, that is the checkerboard, in real time using the camera feed. Using the calibrated camera, the program should then be able to place virtual objects in the scene relative to the detected target, and then these virtual objects should align and orient themselves correctly with respect to the target, taking into account any motion of the camera or the target itself.
So, before moving on to the camera calibration process, our task is to develop a system that can detect the target, that is the checkerboard in the video, and extract the corners of the checkerboard accurately. For this task, I will be following this very beautiful documentation by the OpenCV. Okay, so from this documentation, I learned about a lot of inbuilt function that will be very useful in this project. The first function I found is the find chessboard corner function, and then the draw chessboard corner function, which will be used to find and draw the corners of the chessboard, and to refine the corner positions I will be using this corner suffix function. After that, I will select the calibration images and I will try to calibrate the camera. In order to calibrate the camera, we need to take a lot of pictures of the checkerboard pattern from different angles using the camera. The goal is for the camera to find the pattern in these pictures automatically using OpenCV. Each time the pattern is found in a picture, it provides valuable information that can be used to calculate the camera's internal parameters like camera's focal length and distortion coefficient, which are very essential for accurately placing virtual objects in these scenes. To perform the calibration, we will use this CV calibrate camera function from OpenCV. After that, we will calculate the current position of the camera. In this task, we will write a program that reads camera calibration parameters from a file and then starts a video loop. For each frame captured by the camera, the program will attempt to detect a chessboard pattern. If the pattern is found, it will determine the location of the corners and then use this solve PNP function to calculate the pose of the chessboard, that is basically the rotation and the translation, in real time. After that, we will try to project outside corners, or we will try to project on the 3D axis. In this task, we will enhance our program to project the 3D points corresponding to the 4 outside corners of the chessboard onto the image plane in real time. For this, we will be using this project point function of the OpenCV. After that, we will try to create a virtual object of 3D, which will be made out of lines and project onto the image captured by the camera. So as our camera will move around, the virtual object will maintain its correct orientation relative to the camera. After that, in final, we will detect the robust features. In this task, we will select a feature detection method, suppose Harris corner detection or surface feature detection or SIFT detection, to develop a separate program to detect and visualize these features in a video stream. We will create a pattern of our choice and display the detected feature points on that pattern. Moving forward to the coding section, we first need to calibrate the camera. In order to calibrate the camera, here in the main function, it takes the command line argument. It checks if the correct numbers of arguments are provided and it will exit if not. After that, some variables and objects are declared for the camera calibration, such as params for block detection, corner set and point set to store corner and point coordinates, and camera matrix for intrinsic camera parameters. Then the program initializes a video capture object to read frames from the camera. Inside the main loop, frames are captured from the camera. Then the code performs corner detection on the captured frame using either a chessboard or circle grid pattern based on the command line argument. If the corners are found, the code refines the corner position and draws them on the frame. And then the program waits for a keystroke. If Q is pressed, the program will quit, and if S is pressed, the corners are found and the frame is saved along with the corners and point coordinates. And if C is found and enough calibration frames are saved, camera calibration is performed using the saved corners and point coordinates. The intrinsic camera matrix and distortion coefficients are then calculated, and then the program will output the camera parameters and it will save them to a CSV file, and it will continue until Q is pressed. After that, we will move on to
as soon as we are done with the coding of camera calibration, we will move on to the coding of augmented reality. Here the program expects 2 command line arguments, that is target and object line. Here the target can be either chessboard or the circle grid, and the object name, it will refer to the 3D object file that will be located in the object folder. After that, we will set up the target. So based on the target value, the program sets the dimension of target pattern. For chessboard target, it sets point per row to 9 and point per column to 6, and for circle grid, it will set the points per row to 4 and points per column to 11. After that, the program reads the 3D object file corresponding to the target pattern, and then it populates the vertices and faces vector with the object vertex coordinates and faces indices. And then the program, it will initializes a video capture device CapDAP to read the frames from the camera. And then we will move on to the camera calibration parameters here.
So in this, the program reads the camera intrinsic parameters, that is the camera matrix and distortion coefficients from a CSV file based on the target value, and then the program enters a loop to process each frame from the video stream. And there are some steps that will be performed for each frame. First, the frame will be converted to grayscale for corner detection using and then using OpenCV find chessboard corners or find circle grid function. Corners are detected in the target pattern based on the selected target type, and the detected corners are then refined using the corner suffix for better accuracy, as I said earlier. And depending on the target type, a set of 3D points, or we can say point set, is generated to represent the target pattern's corners, and then the Z coordinate is set to 0 since the pattern is assumed to lie on a flat surface, right? So the program will call the solve PNP here. It will call the solve PNP to estimate the pose, that is the rotation and the translation of the object in the scene using the 2D 3D correspondences, and then the camera intrinsic parameters and distortion coefficients are provided as the input. Then the program will visualize the detected corners on the frame, and it will draw coordinate axis that will represent the object pose using the draw chessboard corners and draw axis function. After that, just the user interface program will wait for the keystrokes from the user, such as if we will press Q, it will quit the program, and if I will play A, then it will show only one axis, and if I will press W, then it will show both the axis, and as well as it will show the 3D object. And if I press S, it will save the current frame as an image. And once the loop ends, the program it will release the video capture device and it will terminate. We can also see the code for feature detection. Here the main function takes the command line argument, so it initializes the mode enum variable m with a default value of Harris. The program opens the video capture device at the camera and check if it is successfully opened or not, and it retrieves the width and height of the frame from the device. Inside the main loop, frames are captured from the camera, and then the captured frame is converted to grayscale, and it will check if the corner detection mode is set to Harris. The Harris corner detection algorithm is applied to the grayscale image using the corner Harris function, and then the corner response matrix is normalized, and the corner above a certain threshold are marked on the frame with red lines. We can change the color to red, blue, green, whichever we want. And if the corner detection mode is set to shift, okay, shift is basically SIFT, scale invariant feature transformation, then that algorithm will be used, and shift key points are detected in the grayscale image using the detect method of the shift feature detector object. The key points are then visualized by drawing them on grayscale image, and after that it's just the user interface, that if we press Q, it will quit the program. If we press S, it will save the current frame. If we press H, the corner detection mode will be set to Harris, and if we press F, the corner detection mode is is made to set to shift. So let's move on to the practical implementation of this project and see how it is working. Whole working of our project, that how our project is working. So first we will go to the folder where our project is kept, and we will open it in terminal. After that we will CMake, and then we will make, and if there will be any errors, it will throw. So here it is 100% done, so there are no errors, and it will generate some executables, and that are generated in the bin. So we'll go in the bin and we'll see for the executables. So here 3 executables are present, that is main for the camera calibration, AR for the augmented reality, and feature for the for the shift and Harris detector features. So first we'll calibrate our camera. So here we will use /main for the camera calibration, and we have to enter the argument, and here we are using chessboard, so our argument is chessboard. So here comes the video. Let me drag it here so that you guys can clearly see all the values also that will be coming. So I think it's quite clear. Let me show if the corners are detecting. Yes. So as you guys can see, the corners are quite visible. Now we will move forward and we will keep pressing S so that it will save the coordinates on the CSV file. It will save all the data. We will save at least 10 times from different angles. Oops. So here, as you can see, I am rotating it as much as possible. Oops, now here it comes again. I think this will be enough for today. I mean, these many pictures are quite enough. Yeah. So now let's press C. It will generate the matrix. Here it has given me all the reprojection error. It is 0.26, which is less than 0.5. It shows that it is good, and it has already generated the CSV. Let's see the CSV. So here is the CSV file. So this is my CSV file that was generated. Now I will move forward to see if after calibration, if the augmented reality is working fine or not. So again, here I will use ./AR, then I am using chessboard as the argument, and my second argument will be what kind of object I am using. So here I have 3 object files. The first one is steady, second one is teapot, and third one is the humanoid. So let's enter teapot and see if it's working or not. Let me increase it for you fully so that you can see. See here, currently it is showing me the axis, right? Now I press A. Now as soon as I will press W, it should start showing me the 3D object. Okay, so see here how beautiful it is. It is showing the teapot. Oh, okay, so the brightness went off. See how beautiful it is, how beautiful computer vision and the augmented reality is. Now let's see the other one. Let's see the humanoid, how beautiful the humanoid looks. As soon as I will press S, it will save, and as soon as I will press Q, it will end. So yes, it is working perfectly fine. Let's see. See, this is the saved picture. Right, now let's see for the humanoid. Now here instead. Okay, so here comes. So let's see this one. So again, first the axis is showing. Now as soon as I will press W, it should show me the 3D object. Okay, so let me reframe it for you so that you guys can see it clearly. Oh yeah, now it is showing perfectly fine. Let me rotate it for you a little bit. The camera is lagging a bit, but I don't think it will be a problem. Yeah, this is good. Now let's see the other one. Let's see the teddy. Let's press Q. Okay, let me maximize this. So here comes the coordinates. Now I'll press W. Okay, so this one is big. Let me go back a bit. So I hope you guys can see this. Just due to the reflection coming from the light. I hope you can see this, how beautiful it is looking, the teddy bear. This is amazing, right? Oh. Okay, so this was the project. Now let's see the features. Let's see if the features are working fine. /features. So you can see here all the corners are getting detected. So now I have pressed H, so it is showing basically the Harris feature detector. It is detecting all the corners. You can see the red dots. Now if I press F, now this is the shift feature detector. Quite beautiful it is. So this was the whole project. I hope you guys have enjoyed this, and in the end I would like to thank my Professor Bruce Maxwell, under whose guidance I have done this project. If you like this video, please do not forget to like, comment and subscribe. Thank you so much and have a nice day. Bye bye.